In this set of notes, we're going to look at a brief introduction to matrix algebra. Matrix algebra can be really useful when it comes to linear regression. In particular, it becomes very useful when we start talking about multiple linear regression and more complicated regression compared to simple linear regression. But we're going to start out this week just looking at some basics of matrix algebra and then looking at how that applies to simple linear regression. So we're going to start out by just defining what a matrix is. So a matrix is a rectangular array of numbers for which operations such as addition and multiplication are defined. And numbers in a matrix are arranged in rows, which are going to be horizontal, and columns, which are vertical. So for example, looking at this matrix that we have right here, these numbers right here, they are the third row, and the numbers going this way, this is the second column. Matrices are usually denoted with bold capital letters, so you'll notice here we have matrix A, and they're framed with either parentheses or square brackets. Data sets can be organized into a matrix where each of the rows represents the subjects and each of the columns the different variables. So typically when you see a data set that you've gotten, this is usually how it's organized. Each of the subjects has their own rows that has all of the measurements for the different variables, and then the columns represent those variables. The elements of a matrix are generally denoted whatever uppercase letter you have for the matrix. We use the lowercase for the individual elements. So for example, in matrix A that we have above, lowercase ij represents the different elements in that matrix. So for example, if we look at A12, that's going to be the element that is in the first row in the second column. So in other words, the 3 that we have right here. So we can say that the matrix, which is an R by C, where little r represents the number of rows and little c represents the number of columns, is equal to the set, so those curly brackets mean the set, of all of the elements for I is equal to 1 up to the number of rows, and j is equal to 1 up to the number of columns. And then the dimension of a matrix is defined by the number of rows by the number of columns. So for example, matrix A that we have up above has 3 rows and 3 columns, so we would say that it is a 3 by 3 matrix. So we have some definitions here. A square matrix is any matrix where the number of rows is equal to the number of columns. So for example, B that we have listed here is a 3 by 3. It is a square matrix. We could have, for example, let's do another matrix. C is equal to 1, 2, 3, 4. This would be an example of a 2 by 2 matrix. A column vector is a matrix with dimensions r by 1. In other words, it only has one column. Whereas a row vector is a matrix with dimension 1 by c. In other words, it only has one row. And then a transpose matrix is a matrix that's defined by either of these notation and is found by interchanging the rows and the columns. So for example, in matrix E, notice that the first row has the elements 3, 13, and 6. So the first column of E transpose will have the elements 3, 13, and 6. We can perform arithmetic on a matrix. So in order to add or subtract two matrices, they do have to have the same dimensions. So looking at an example, notice that matrix A is a 3 by 3 and matrix B is a 3 by 3. So since these have the same dimensions, we can perform arithmetic. And matrix arithmetic is pretty intuitive. What you do is you find each of the elements in the corresponding or in the same row and column. So for example, the element A11 is 23 and the element B11 is 3, and then you add those together. So we have 23 plus 3 gives us the 26, 3 plus 1 gives us the 4, and so on. So pause the video for just a moment, see if you can add together these three matrices. and then when you unpause the video, I'll work through the solution. Alright, so we are going to add together A plus B plus C. Well, first of all, notice that A is a 2 by 3, B is a 2 by 3, and C is also a 2 by 3. So since these are all of the same dimension, we can add them all together. And so I know the resulting matrix is going to be a 2 by 3. So now I'm going to go through and add all the elements. So starting here, we have 5 plus 0 plus 13 is 18. 1 plus 1 plus 1 is 3. And going through the rest, you should find the following. In addition to arithmetic, we can also do multiplication. Multiplication for matrices is a little bit more complicated than the arithmetic. We can't just go through and multiply the corresponding elements. It is a little bit different, so we're going to look at some examples. Now, the first type of multiplication you can do is just multiplying through by a constant. And multiplying through by a constant is more intuitive. It is what you would think it is. So for example, we have matrix A here. If I want to multiply by the constant c equals 2, and I should note here in the notes I've used lowercase c for two different things. One to denote the number of columns, the other one to denote a constant. So keep that in mind. So in context we'll tell you which one we're using c for. So we have matrix A, we're going to multiply it by 2. Well, in order to multiply by the constant, we do just go through and multiply each of the elements by 2. So for example, 23 times 2, this should be 46. I'll correct that on your PDF. 12 times 2 is 24, 1 times 2 is 2, 3 times 2 is 6, and so on. Now, multiplying two matrices together is what gets a little bit more complicated. So in order to do that, we first need our two matrices to match as follows. So in order to multiply them, we need the number of columns in the first matrix to equal the number of rows in the second. The resulting matrix will have the same number of rows as the first and the number of columns as the second. So one way to think of this is if we were to write out the dimensions of the first matrix, and then we wrote out the dimensions of the second matrix. In order to perform matrix multiplication, we need these two numbers to match, and then these outer two numbers, these are going to tell us the dimensions of the product. Alright, so we have some steps here to help us multiply two matrices together. The first one is to determine the dimensions of the resulting matrix. Then what we do is we multiply each element of a row in the first by the elements of the column in the second. For each product of rows and columns, we calculate the sum, and then that sum defines each element of the resulting matrix. So this sounds like a lot, but after you do a couple of these, it's not too bad. So let's look at an example here. So here we're going to multiply E by C. So notice that E is a 2 by 3 matrix, C is a 3 by 1. So using our rule that we saw earlier, if we write these side by side, we have a 2 by 3 and a 3 by 1. Notice that the 3's match, so that tells us we can perform matrix multiplication. And then using the outer numbers, the 2 by 1, that actually tells us the dimension of our product. So notice here, if we multiply E by C, that's going to result in a 2 by 1 matrix. Next, we can start to find the elements. To do this, what we're going to do is we're going to multiply each of the rows by the columns in the second matrix. So the first matrix has 2 rows. The second one has a single column. So what we're going to do is we're going to take this column times the first row. And so notice if we do that, we get the following: 3 times 3, 13 times 4, and 6 times 56. We're then going to take this column times the second row. In doing this, we get 1 times 3, 11 times 4, and 5 times 56. In step 3, we calculate the sums across, and then this is going to define the elements. So here we have E by C, or E times C rather, and notice that is a 2 by 1 matrix. So let's look at another example. We're going to multiply the following two matrices. Notice that A is a 2 by 3 and B is a 3 by 2. Since these two numbers match, we can perform multiplication, and the outer two numbers give us the dimensions of our product. So here we know that if we take A times B, that is going to result in a 2 by 2 matrix. So let's see how to do this. So looking at A times B, the first thing we're going to do is we are going to take the first row of A times the first column of B. So the first values we are going to have are 5 times 0 plus 13 times 3 plus 6 times 6. And that's going to end up giving us our first element of our new matrix. Next, we're going to take the first column of B times the second row of A. So here we're going to have 1 times 0 plus 6 times 3 plus 5 times 6. Next, we're going to do that same process, except now what we're going to do is we're going to look at the second column of B. So we're going to take the second column of B times the first row of A. So we're going to have 5 times 1 plus 13 times 0 plus 6 times 5. Then we're going to have the second column of B times the second row of A. So we're going to have 1 times 1 plus 6 times 0 plus 5 times 5. Now we're going to find the sums to find our matrix. So the first element is going to be equal to 5 times 0, which is 0, plus 13 times 3, which is 39, plus 6 times 6, which is 36. This results in 75, where they're going to have 0 plus 18 plus 30, which is 48. Next, we're going to have 5 plus 30, which is 35. And we're going to have 1 plus 25, which is 26 as the last element. And notice our resulting matrix is a 2 by 2 matrix. Next, we're going to look at some more special types of matrices. A square matrix is considered symmetric if it is equal to its transpose. And so here's an example. Notice if we take the transpose of A, we get the same matrix, so we consider this symmetric. Another way to look at this is the diagonal of each of these matrices is the same, but then also within a matrix, notice if we look at the off diagonals mirror one another. So we have 45, 45, 4, 4, and 12, 12, and this is the same for both of these matrices. A square matrix is considered a diagonal matrix if all of the entries other than those on the main diagonal are zeros. So when we mean the main diagonal, this is what we mean, is this diagonal right here. And notice all the other elements are 0. An identity matrix is a diagonal matrix where all the elements in the diagonal are equal to 1. And this is what we would call a 3 by 3 identity matrix. A scalar matrix is a diagonal matrix where the diagonals are equal to some constant, where that constant is the same for all of the elements in the diagonal. So if C is equal to 1, we then have an identity matrix. And then the null vector is a row or a column vector of all zeros. Another concept we need to talk about is the concept of linear dependence. So a matrix can be viewed as a set of column vectors. For example, the matrix A that we have here could be separated into these 3 column vectors. If we let V1 through Vp denote the column vectors of the matrix, we say the columns are linearly dependent when a set of scalars, which are not all equal to 0, exist, so that we could add these up and they equal to 0. If that relationship only holds when all the c's are equal to 0, then we say the columns are linearly independent. So let's look at an example. We're going to show the columns of the following matrix are linearly dependent. So let's first look at what our three vectors are. So our first column vector is 1, 2, and 0. Our second column vector is equal to 3, 1, and 2. And our third column vector is equal to 9, 8, and 4. All right. Notice here, if I take 3 times v1 plus 2 times v2, I get the following. So, what this tells me is I can find a combination of the first two vectors that are equal to my third vector. Therefore, these are linearly dependent. So in this case, what we would be saying is that my first constant is equal to 3, my second constant is equal to 2, and the third constant is equal to -1. Because notice, if I take c1 times vector 1 plus c2 times vector 2, and then I subtract off my third vector, that would be equal to 0. The rank of a matrix is the maximum number of columns that are linearly independent. All right, our last topic we need to talk about here is what we call the inverse of a matrix. The inverse of matrix A is denoted as follows. The inverse is only defined for square matrices, but not all square matrices will have an inverse. When a matrix is multiplied by its inverse, the resulting matrix is the identity matrix. So we get this property right here. A matrix is called non-singular or full rank when the rank of the matrix is equal to the number of columns in a matrix. So in other words, what we're saying is that all of the columns are independent of one another. We can't have one column that's a combination of the others. And a matrix is singular when the rank of the matrix is less than the number of columns. If a matrix is square and non-singular, then the inverse exists. So we're just going to look at how to find the inverse of a 2 by 2 matrix. Finding inverses for larger matrices can be more difficult, and we can use software to help us with that. So here's how to find the inverse of a 2 by 2 matrix. If we define our 2 by 2 matrix as follows, here is your formula for the inverse. Now this piece right here has a special name that is called the determinant for a 2 by 2 matrix. So let's find the inverse of the following matrix and confirm that when we take the matrix times its inverse, we do in fact get back the identity matrix. So the first thing we're going to do is we're going to calculate the determinant. Okay, so we know that the determinant is equal to A times D minus B times C. So for the A, the D, the B, and the C, we look at this relationship that we have up here. So notice for this example that A is equal to 4, B is equal to 3, C is equal to 1, and little d is equal to 2. So filling that in for our determinant, we are going to have 4 times 2 minus 3 times 1. So 8 times 3 is equal to 5. So now we can find our inverse. So we have A inverse. So the first thing we're going to do is we're going to flip the values that are on the diagonal. So we're going to have 2 and 4. And the numbers on the off diagonal are going to become negative. And then we need to divide all of these numbers by the determinant. So that is the inverse. So let's now confirm that A times its inverse is equal to the identity matrix. So first, writing down A. Next, writing down the inverse. And then next we can perform matrix matrix multiplication to confirm this is the identity matrix. Notice we have a 2 by 2 times a 2 by 2, so the resulting matrix will be a 2 by 2. So performing matrix multiplication, we have the following. And we find that this is indeed the identity matrix, and this is the 2 by 2 identity matrix. And then we could also go the other way and take A inverse times A. So if you want to try that on your own, and you would also find that that is equal to the identity matrix. So this is going to conclude this note set.